Good. So let's continue with model validation and selection. So I have again here a scatter plot of a data set. We have a single feature X. Let's just call it X. And the label Y. So we have some data points here. So let's say this here would be the data point feature 1, label 1. And then I plotted two hypotheses. So how do you think this could be examples of a linear model, these two hypotheses? Could this pink and red curve both belong to the set of linear maps, linear function of the feature X? No. So this here is linear. So this here is this hypothesis here belongs to, and I call this the hypothesis space of linear maps is the space of polynomials of degree 1. Yeah. And pink, so pink you could get from, let's say, this could be a hypothesis in a polynomial set of polynomials of degree 10, let's say. So which one do you like more? Let's say you have trained them, they are obtained by minimizing the training error. Which one? So this one you got, so this red one, let's say you got from linear regression dot fit, and this pink one you got from polynomial regression dot fit. So you trained two different models, and you got the red curve from the fit function and the pink one. Yeah, there are some comments. The pink one seems to be overfitting, but how do you know that it overfits? How do you know that the pink one is overfitting? If I only have the training set, the blue data points here, the blue dots, if all I have is this training set, how can you tell that the pink one is overfitting? There's no way. Yeah, you need to assume a bit more. You need to assume something. In machine learning applications, you don't only have data. If you only have data without a model, you cannot do much. You can send it, you can attach it to an email, a CSV file with the data, you can print it out, put it onto your walls as posters, the data. You always need a model. You always need to interpret the data by fitting it against the model. And one widely used model is, or modeling assumption is that if you vary a bit the data points, then or if you vary the features a bit, if you wiggle around here, then the label should not change too much. This is kind of a robustness assumption that is often used. But a more principled approach is that you say you try to gather other data points, additional data points like this here. You collect a bit more data and use this as a validation set. So you use a validation set, and the validation set is any set of data points that you didn't use for training, period. As soon as you didn't use a data points as for training, you can use it as a validation set. And then you might spot here, you get a large validation error. So you typically use the same loss. So you use here the squared loss, y hat minus y square on the validation set. And since we only have a single data point in the validation set, there's no need to average. If we have more data points, let's say we would have here another validation data point, we would also compute the squared error here and then compute the average loss over the validation set. So what we get in the end is two numbers for a single model. So a model might be all polynomials of degree 10. First, we train the model. We learn the best degree 10 polynomial, the pink curve, get a training error, a small training error typically, and then we validate it. So we get a validation error, which is the average loss on the validation set. And we also got the training error. So we compute the errors also on the training set, but this is rather small. So we also get the training error, which is the average loss on the training set. So, and this is basically stage 2 of the machine learning project. Compute the training error for one specific model, like degree 10 polynomials, and the validation error. That's basically the whole content of the stage 2 of the machine learning project. We might also ask you a bit to interpret the results. So you can diagnose machine learning methods, like you use polynomial regression with degree 10, by comparing the training error and the validation error. So you look at 2 bars, so to say, the training error, which is typically small because modern machine learning models are powerful. They are large. They have many degrees of freedom, a large complexity, and the validation error. So this is the validation error. And if the validation error is much larger, there are no apps. I cannot tell you precise rules. So let's say, is it 50% larger, 100% larger? This depends on the application. But if it's significantly larger, roughly speaking, the validation error is significantly larger than the training error, then this might be an indicator for overfitting. And what we then do is we try to bring down the validation error even at the cost of incurring a higher training error. So how can we bring down the validation error by making a bit of sacrifice on the training set? How can we make the training harder, so to say, with the hope that the learned hypothesis is good outside the training set? What are the options, the technologies to do this? Use a smaller model, yes. For example, use, instead of degree 10 polynomial, use degree 1 polynomial or linear maps. Yeah, so linear. And here for this linear curve, the optimal hypothesis that we got for linear, we might have a higher training error, but the validation error of the linear function might have gone down. So this was already an improvement, because ultimately the validation error is the estimate for the performance of the learned hypothesis outside the training set. And you are always interested what happens outside the training set. You're not interested in perfectly doing on a training set. You want to learn a hypothesis that generalizes beyond the training set. So the validation error is the important quantity, not the training error. In most cases, with modern machine learning methods like deep neural networks or even linear regression with many features, when you use many features, and we can simply compute so many features, just look at the webcam snapshot with millions of pixels. So you get a feature vector of length millions. And this means that the resulting hypothesis space of linear maps is very large, it has a large dimension or effective dimension. And whenever you have a model with such a large dimension, you will easily find one hypothesis that perfectly goes through the training set. So the training error will be essentially 0 in many cases. But this doesn't mean much. This only tells you that you were able to use the .fit function of that powerful model or method. So what you then typically get is a large validation error. And how to bring down the validation error? Well, use a smaller model, or what's the dual approach? Instead of using a smaller model, what could we do? Use more data. Use more data. Yeah, soft pruning is just a more elegant way to use a smaller model. But the dual approach looks at the data aspect or the data component. So alternatively, we could collect more data points, but we don't even need to collect more data points. We can just say we want a learned hypothesis to be robust against small changes, so we can augment the data points by taking each original data point and add a new data point by leaving the label untouched. So here, this is the same label value, but wiggle around a bit the features, so add a bit of noise. Okay, this is called data augmentation. So that's how you get larger training sets. Even it's only artificial data, but it might be useful. It is useful already because when you use such augmented data, you kind of enforce or you favor a hypothesis that is not changing too rapidly. So you build in via the data, you build in via choosing the data set or creating a data set, an augmented data set, you build in the requirement that you learn a hypothesis that doesn't change too widely. So for example, this pink curve might not be the learned hypothesis anymore, even if you use a model, even if you use a degree 10 polynomial model, but it might be that the best degree 10 polynomial looks like this. So way nicer, more behaved, so to say. And this you do only by adding more data points. So you don't need any model redesign or any tricks regarding optimization. All you do is you add a bit more of noisy data points. And you force the learning algorithm to come up to learn a nicer or a smoother hypothesis map. So data augmentation is the alternative approach. Either you make the model smaller or data augmentation. And these two components come together in regularization, because when you look at the training error that you get, so let's say that this blue or light blue data points, they are original data points, or the actual data that you collected, the real world data, whatever that means. So you would get the training error would be a term like this. So you have, let's say, M raw data points, you have your hypothesis, and okay, let's stick to the squared error loss for simplicity, minus the predicted label to the power of 2. So this would be the training error. And now say okay, let's use a different color. We augment these original data points by small perturbations. And these new data points, of course, when you add it to the training set, you get also additional terms here. So you get additional terms for each original data point. You get the number of copies, or let's call it augmentation parameter. Let's say for each original data point, we add 2 new data points. We augment by 2. So B would be 2. So we get the label of the original data point, which is the same. We don't change the label, minus this predictor function, the hypothesis that we would like to evaluate. How good is it? And we take the original feature plus this small error term here that we add, because we add a bit of noise. So we add a bit of noise to the ith data point, and this is the jth realization of the noise. So this is noise term. Okay. And if you then let this augmentation parameter go to infinity, you can approximate this sum here by an expectation. And it turns out that this expectation for linear maps is something like a constant times the weight squared. Okay. So what you get in the end, when you look at these additional loss terms that you get from the augmented data points, you get ridge regression. So you get the objective function is then the plane training error. So you compute the training error using your real world data points, the actual collected data points, plus then this term, which comes from these augmented data points, and you approximate the sum that comes from that reflects the augmented data points by an expectation. And if you evaluate this expectation, what you get is some constant, let's call this constant lambda, times the weight vector squared. So here we assume that that the map is linear. So it's a linear hypothesis map. Okay. And this is the objective function that you want them to minimize. And this is called ridge regression. So I'll show you that this is also allowed. We have it here. So this belongs to the allowed methods. I think it's a linear method called ridge regression. Ridge. Yeah. So here, this term here, what I showed you is this regular training error, the average squared loss on the training set. And this term here, this regularization term, turns out to be an estimate for the additional loss that you get from adding perturbed data points from this data augmentation. Yeah, so this combines, this shows that data augmentation is actually the same as model pruning, because when you have some background, and this is way beyond the scope of this course, but when you look at this optimization problem, what this term here is actually it's kind of a penalty term for enforcing a constraint, so requiring the weights of the linear hypothesis to be not too large or to belong to a subset. So you basically constrain the optimization problem to only consider linear maps with a small weight. So this is essentially the same as pruning the hypothesis space. Why is a smaller W is better? Yeah, why is a smaller W better? Why do we want to have a smaller W? Let me show this here in my artwork. Why do we penalize the weight vector? So why is it better to have a smaller weight? Because we say we want to minimize this training error plus weight to the power of 2. So this means we penalize large weights. We want to keep the weight. We want to learn a hypothesis which has a small weight. So why? Because if we augment the data points like this horizontally, and you use more and more of these data points, so what you essentially do is you smear out your data set to become basically a horizontal line. Okay, so the best hypothesis must be essentially a horizontal line, and this W is the slope of this line, so it must be flat. So this is why the weight tends to be then smaller, because this augmentation by the specific way of augmenting data points, by leaving the label value the same, but wiggling around the feature values. So we smear out the data points on the horizontal axis, and therefore we also favor to learn a hypothesis that is more flat. So we smear out the data points horizontally, which favors then a hypothesis that is also more horizontal and not like steep. And this means that the weight must be small. Yeah, to give you some intuition for this behavior. Okay, so what I have talked about so far is mostly about bringing the validation error down, so avoiding overfitting. Let me now, in the final part of this lecture, look at another problem, which is called underfitting. So let's consider a data set that looks like as follows. Here we have data points, and here we have data points. And I used a linear model. I used linear regression, and this linear regression gave me this function. So I used linear regression.fit train to find a hypothesis that has minimum average squared error loss for this data set. Okay. And it turns out that the training error is rather large. So the resulting training error is large. Yeah, first of all, how do you know if the training error is large? This might already be difficult to find out. This also needs training or experience as a machine learning scientist. How do I know that this training error is too large? Do you have, what would be the most simple way to find out that the training error could be smaller? So let's say overfitting is for sure not an issue. Let's say the validation error is on par, is on the same level as the training error. So there's no overfitting going on. How could we know? How could we find out that the training error is large? Yeah, one way is to use a probabilistic model. A probabilistic model, try to estimate a probability distribution or fit the probability distribution, and then use optimal probabilistic methods. But let's say this is too complicated. What is an even simpler approach? How could I know that there might be another hypothesis with a smaller training error? Well, linear regression only searches over the set of linear maps. So what could I do to explore beyond linear maps? Yeah, try polynomials, exactly. So you could say, well, it seems there's no overfitting, but there might be still some room for improvement by using a larger model, by using for example, a polynomials of degree 3. So then you get maybe, let's stick to pink, this one here, and you get a smaller training error. But yeah, and then hopefully you also get the validation error down, but it might be that actually you then hit the point where you overfit. So the validation error increases, which is what you don't want. But it might also be that simultaneously with bringing the training error down, you also get the validation error down, because you reduce the underfitting. This is called underfitting. If you have too simple, if you use a too simple model, which is not able to capture some nonlinear relations. Okay, but here, what I would like to show you is one funny way to make use of clustering. So what you could do is, when you look at this data, and it's always advisable to look at the data trying to make a scatter plot. But for making a scatter plot, you need to represent data points by two features. So by two numeric features. Do you know how to transform data points which consist of thousands? Yes, PCA. Okay, so it seems I can speed up a bit. This is one use of dimensionality reduction, to get two features, and then you can plot it as a scatter plot. So, but let's say we have now these data points, and what you could do is you could say, okay, this looks like there are two regimes. There are two regimes where in each regime I could find a good linear map. And these two regimes, actually, I could find, how could we find these two regimes? There seems to be two groups of data points in the scatter plot. How can we find groups which are more similar to each other within the same group than in the other group? Clustering. So what we could do is, and which clustering method did you hear about recently? KNN. Yeah, KNN is so KNN is rather a supervised learning method. So you try to predict the label. K-means, yes, K-means. So what we could do is we could use K-means or dbScan, yes. We could use K-means, feed this data set in and treat the label value as a feature. So we do as if the label value, this vertical coordinate, would be a feature. So we could use K-means and find this cluster and this cluster and corresponding cluster means. So we get a cluster mean here and a cluster mean here from K-means. And what we could now do is we could create a new feature. We could say each data point that comes in, new data point, we look at the feature, the original feature X, and see which one of the two cluster means is nearest. So we define a new feature, X, let's call it X2. New feature of a data point, which we define by is, let's say, 1 if the raw feature of the data point X is near cluster mean, let's call this M1, near M1, and 0 otherwise. So if it's nearer to cluster mean M2. So we encode the cluster membership of a data point as a new feature. And we could then use this new feature to choose between different weights of a linear map. So I might make this actually an exercise to then use this new feature to combine, to feed in the new feature vector, or a data point is now characterized by a feature vector of length 2. We have the original raw feature, X and X2. Remember, a feature, we can compute features. So you are free to choose what features you want. You can engineer features. And one way to engineer features is, for example, look at the clustering or cluster structure of the data set, and then use the cluster assignment of data points as a feature. And then we feed in this new feature vector into linear regression. And then it might be possible actually that using this combination, so you first map the single feature into a feature vector, which contains the copy of the feature itself and X2, the new feature, which is the cluster assignment. And using these two features, you might get a hypothesis that looks like this. So although it is linear, so this is, let's call this new feature vector X tilde. This is linear, a linear map in X tilde, so H of X tilde. It is non-linear in the original feature in X. This is the advantage when you go to higher to more features. What is the name of methods that use infinitely many features, that push this to an extreme? So they don't use a finite number of more features, but they map the original feature into an infinite dimensional space. How are these methods called? This map is known as a kernel map. So these are kernel methods. And this is, again, way beyond the scope of this course, but they are advanced courses that focus on machine learning methods that use this trick to map the original features, might be one or several original features, to a much, much longer feature vector. Because then in this longer feature vector, you can always then just use linear maps, use linear regression using this new longer feature vector. But from the original feature perspective, you get very complicated. You can learn very nonlinear functions. Like in this case here, we can learn this piecewise linear function in the original feature. But however, this piecewise linear function would look like a linear function in this new feature space that also consists this new feature X2. Okay, and this way, for example, so adding new features is also a way to bring down the training error. Yeah, in this case, in this extreme case, pathological case, training error would now become 0 using this additional feature and linear regression. Okay, so that's basically the overview that I wanted to talk about today. So let's now, for the last few minutes, I'll focus on your questions. Please go ahead with any questions that you have.